Hey everybody, welcome to our next video, which is all about specific heat capacity. Before we get into that though, I just want to differentiate between two different terms that you're familiar with hearing. I know you're very familiar with hearing both of these, but I just want you to understand what the difference is between each of them, which you might already understand, but it's crucial that we really get that down pat in order to understand specific heat capacity. So let's talk about temperature first. You're very familiar with measuring the temperature of a system and grab a thermometer. What is the temperature reading? Well, the temperature of something is a measure of the amount of kinetic energy the particles have within that system. And it also tells us how hot or cold something is. So the more energy the particles within a system have, the higher the temperature that they have, because that's literally what a thermometer measures, is the amount of movement that's occurring within those particles. So we do that with a thermometer. Like I said, that's the temperature of something. Temperature is a measure of kinetic energy. Whereas heat is a measure of how thermal energy flows within a system. So objects can gain or lose heat, but they cannot have heat. They have a temperature, so they have a certain amount of energy that those particles have, and they can transfer some of that energy via heat. So it's how much energy flows within a system. Now you could feel the heat of something if you put your hands next to a fire. You are actually feeling the heat coming from that. That energy from that fire is transferring to your hands. So that is how energy is flowing from the flame into your hands. That is what heat is. And we are going to use both of these in order to talk about specific heat capacity. So what is it? What is the specific heat capacity? Well, it's the amount of heat that's required. So it's the amount of the transfer of energy, the amount of heat that's required to raise the temperature of something of 1 gram of that substance by 1 degree Celsius or 1 Kelvin. And we could say the same unit for that because they're both on the same scale. 0 degrees Celsius is 273 Kelvin. 1 degree Celsius is 274 Kelvin. It's on the same scale. So how much heat is required, or how much heat must be applied to something in order to raise 1 gram of that substance by 1 degree Celsius or Kelvin? And the equation looks like this. So the equation is Q equals mc delta T. Q is the heat that's either required or absorbed in the reaction. Now, you might hear me use energy or heat, and that's because in this class, they're going to be equal to one another. So Q is the heat that's either required or that's absorbed in the reaction, whether it's lowering its temperature or whether it's getting a higher temperature. M is the mass of the substance. So of course, it's going to take a lot more heat to raise the temperature of the ocean than a glass of water. And that's because the ocean is much larger. So we do need to have a unit of amount in there, and we use the mass in this case. C is the specific heat capacity, and the specific heat capacity has very specific units, and the units for this value are joules per gram degree Celsius. And I don't have this on the slide, but Q should have units of joules. Hopefully it is in your notes there. Q, or heat energy, should be in units of joules. Mass, of course, is the mass in grams. So therefore, your specific heat capacity is in units of joules per gram degree Celsius. So joules is a measure of energy. And of course, we're trying to measure how much energy is required to raise 1 gram of the substance. So that's what that lowercase g is for, by 1 degree Celsius. And it's unique to that substance and that phase, which we're going to see on the next slide here. And delta T is your change in temperature. So that's what delta means. Whenever you see that triangle, delta is just the change in. So it's the change in temperature. And normally we denote delta T by final minus initial. So the final temperature minus that initial temperature. And here are just some specific heats for some common substances. What has the highest specific heat is water. Water in every state of matter has a very high specific heat. It takes a lot of energy to raise the temperature of water by 1 degree Celsius, 1 gram of water by 1 degree Celsius. And that's because you have to break some hydrogen bonds to do that. And because it's a measure of kinetic energy, because temperature is a measure of kinetic energy, to get those particles to move faster, you have to break some hydrogen bonds. And that takes a lot of energy to do that. So the specific heat of liquid water in particular is very high. It takes a lot of energy to raise liquid water by 1 gram of it by 1 degree Celsius. You'll see ice has a different specific heat, not as high as liquid water, but still pretty darn high. Water vapor has a little bit of a lower specific heat, but please note that there are different values for each state of matter. And as you progress through this list, you will see that there are different compounds in their different states of matter. So there's ammonia, there's benzene, ethanol. Notice how your metals and your covalent network solids have very low specific heats. It does not take a lot of energy to raise the temperature of those substances. If you were to heat a pot of water on the stove to boil something, to make macaroni, whatever, that metal pot gets hotter much faster than the water that's inside of it. And that's because it does not take as much energy to raise 1 gram of that metal by 1 degree Celsius. It takes a lot more energy to raise the temperature of water, which is why when you're starving, I hate waiting for the water to boil when I'm super, super hungry, because it takes a lot of energy for water to boil. It does not take as much energy, however, for some of these metals down below. Let's go ahead and talk about the value of Q before we get started in some of these samples problems. So when heat is being applied to something, your Q is going to be a positive value. Whereas when heat is being released, Q is a negative value. So again, Q is the heat energy. When I am applying heat to something, Q is going to be a positive value, and that's because the heat is being absorbed by the system. Whereas when heat is being released, when something feels warm, right? When something is very hot, so if you have a hot pot and it's releasing heat to your hands, Q is going to be a negative value. So we do need to get familiar with those semantics. So positive and negative values for Q. So here's just a little image that I saw. It doesn't have to be a gas necessarily, but if we apply heat to this system, Q is going to be positive. So it is a positive heat. However, if this is very warm and it's releasing energy to the environment, that Q is going to be a negative value. So Q is negative when it is releasing heat. Q is positive when that substance is absorbing heat. Knowing that information, let's go ahead and do the sample problems in the notes together. All right, so let's jump in here and do sample problems 10 through 12. So all of these problems are using that same equation. And that equation is Q equals MC delta T. So let's just go ahead and get this up on the screen here so we remember. But we are always using Q equals MC and delta T, where Q is the amount of heat that's being added to the system or the amount of energy that's being released. So before we dive into these particular sample problems, let's just get some semantics for Q down. So those positive and negative values. we have to remember that Q is going to be a negative value, and that is when energy is being released. Energy is released from the system. And when energy is being released, that's when your temperature is actually going to go down. Because, of course, since temperature is a measure of kinetic energy, if your temperature is going down, then, of course, that energy has to be released. And when energy is released, we use a negative value of Q to represent that. On the other hand, your Q is going to be a positive value, and that's when energy is absorbed in the system. Energy is absorbed. So when energy is absorbed, that's when T is going to be increasing, because again, since temperature is a measure of kinetic energy, then if I'm increasing the temperature, the amount of energy that those particles is also increasing. So it's absorbing energy from the surrounding environment. So let's just keep that in mind as we progress through these sample problems together here. So calculate the amount of energy that's required to raise the temperature of 14 grams of water by 3 degrees Celsius. And we have that specific heat of water, which is a constant, that's always 4.184 joules per gram degree Celsius. This is a nice and easy problem, actually, because it just tells us that we're raising the temperature by 3 degrees. So this right here is our delta T. Right there. We don't have to do any subtracting for that one because we're just raising it 3 degrees, so it doesn't matter. M is actually 14 grams right here, so that's going to be equal to our M. And C is 4.184. So this is a nice and easy one because I have everything that I already need in this particular problem. So M is equal to 14 grams. C is 4.184, and delta T is 3 degrees Celsius. Now, because we are raising the temperature, energy is being absorbed in the system. So our Q is going to be a positive value in this case. And unfortunately, and even for me, I still have to really think about each of these things, that Q is positive when it's absorbing energy. So I even have to sit back and say, okay, is Q positive or negative? In this case, it's positive because it's absorbing. And we're going to see in some problems as we progress through this thermochemistry stuff that your delta T may be negative, which means that Q is negative. Anyway, your answer here, Q is equal to positive 176 joules. And the units work themselves out nicely. So just off to the side here, I'm going to show you why Q is in just units of joules. So your M is units of grams, right? And technically that's over 1 because anything is over 1. In your C, specific heat, that's units of joules per gram degree Celsius. And then I have degree Celsius here. Notice how in this mass portion, that's grams is on the top, but in specific heat, grams is on the bottom, so they cancel each other out. And the same is true for degrees Celsius. So you're left simply with units of joules for that heat value. So the units always work themselves out as you go through these as well. When I was in grad school, that was something that I always focused on myself, was making sure that my units always canceled out, because then you knew if your units cancel out, all right, then I'm probably at least much closer to the right answer than I think I am. Let's try sample problem 11, and I'm going to keep this down here on the screen because I just want to show this up here for this one as well. Calculate the heat required to raise 5.39 grams of water from 21 degrees Celsius to 33.7 degrees Celsius. So again, it does say we are raising the temperature of water. So energy is being absorbed, which means Q is going to have to be positive. And that's just something to consider as you're going through this problem. But really, we're going to get a positive value anyway. We have to remember that delta T is going to be equal to your final temperature minus your initial temperature. And in this case, I'm raising water from 21 degrees, so that's my initial temperature, to 33.7. So 33.7 is my final temperature. So it's very similar to sample problem 10, but in this case, we just have to plug in that delta T portion instead because we're not given just that it's being raised by 3 degrees. So we're going to use Q equals MC delta T. Q is equal to the mass, which is 5.39 grams. Still water, so I'm still going to use 4.184 joules per gram degrees Celsius. And delta T, remember, is the final temperature, so 33.7 degrees Celsius minus that initial temperature. So when you solve for this anyway, you're going to get a positive value, and it's always good to just double check that. And when you do solve for this, you should get Q is equal to positive 286 joules. So you would have to add 286 joules of energy to raise 5.39 grams of water by, in that case, delta T is equal to 12.7. So that's it for that one. Let's go ahead and try sample problem 12, which is a little bit different because we're actually solving for one of or part of delta T in this case rather than Q itself. So calculate the final temperature right here. Calculate the final temperature. So we're going to find TF. TF right there. When 1,250 joules of energy is removed, so I'm removing that much energy. So if energy is being removed, we know Q must be negative in this case. And this is where this thermodynamic stuff can get confusing, and it's always important to recognize positives and negatives. So because energy is being removed, I know my Q must be a negative value from 6.39 grams of water at 50 degrees. So I do know that the temperature must be going down, right? So because I'm removing energy from that. Let's go ahead and get all of my variables in here. We're still going to use Q equals MC delta T. And I actually have Q right here. And it's not telling us, but remember, this Q must be negative because I'm removing that much energy. If you can still do this if you forget the negative, but I think it's harder to just keep all of your numbers straight as you're doing this. So if you can just remember removal is negative, absorbing is positive, I think this makes it that much easier for you. So there's my Q. And again, it's releasing energy. It's being removed, so it's negative, is equal to M. In this case is 6.39 grams. C, we're still talking water here. So this value is not always going to be water, but it happens to be because all three of these problems deal with water. In the liquid phase, if it were other phases, it would be a different value. And so again, we're trying to find delta or T of F. So I am just going to solve for TF. And I know that my initial temperature is 50 right here. So it's starting off from 50 degrees right here. And I'm going to solve it this way. Now you could solve for delta T and then do that at the end and then find the value that way. I just like to do it all in one shot. I mean, that's just my personal preference, but ultimately it's up to you, however you want to solve that. So I'm going to solve this by multiplying these two values first. So I have 26.736, and I'm not adhering to sig figs here because I'm just trying to solve the problem. And then I have TF minus 50, and that's equal to negative 1250 joules. It doesn't even matter about units there really. Now I'm going to solve that next part. I'm going to divide both sides by 26.736. So let's solve that on my calculator here. And when I solve for that, I get, again, I'm not adhering to sig fig rules just yet. I'll do that at the very, very end. 7, I'll just do 753 is equal to TF minus 50. And then, of course, to isolate TF, I'm going to add 50 to both sides. So when I add 50 to both sides, I get 3.2. And I'm going to keep mine here to just one place after the decimal because that's the rule when you're adding. So yeah, so delta, your final temperature would be 3.2. So in this case, it happens to work out. So you could solve for delta T if you want to, but I just, because I know delta T is equal to the final temperature minus the initial temperature, I just plugged that variable in and I solved it that way. And I found that when I remove 1,250 joules of energy from that size sample of water, the temperature of water goes down to 3.2 degrees Celsius. We're going to do lots of practice with this in class. I hope for us to do quite a bit of labs with this as well. But as always, if you have any questions on this, let me know. Stop by and see me. And if not, I will see you in the next video. Bye.